What's going on, people? So today I'm doing the daily problem from LeetCode. Okay, so I did it. I was gonna try recording myself doing it live, but it was taking too long, so I'm not gonna do that. So I'm just gonna go over what code I ended up with. I mean, when I say take too long, I don't mean like it's taking me hours. I just mean like I want a recording that's like less than 20 minutes or less than 10 minutes preferably. So instead, what I'm doing is I'm just going to go over the code that I ended up with. So, using. So, okay, so this passed all the cases. I kind of had to do this, so here's what we did. So first off, I'll go over the problem. It's just, the problem is binary tree level order traversal, and you're doing a level order traversal on a binary tree. So this is not a binary search tree. Also, because it's a binary tree, that means that it doesn't tell if it's balanced or we don't know. This could be a skew tree, and a skew tree just means it goes like, imagine 327. That'd be a skew tree or whatever. Yeah, so like a skew tree is like the opposite of being balanced. Balance is like, means, oh rats. Hold on. What did I just do? Oops. Right, okay, so, whoops, what happened? I went off the problem? Okay. So, yeah, so anyways, I want to basically do a level order traversal, which is like a BFS, so okay. But then the thing is you want to do a bottom up. So my approach is just do a regular BFS and then reverse it. So I do, if not root, and so I return an empty list if there's no root. But I start a deck. I use a deck because a deck works very well for BFS search in Python. It allows me to use the FIFO property, and a FIFO is what you want for a BFS. FIFO is also sometimes called a queue, and FIFO just means first in, first out. And you can do first in, first out because you can pop from the left with the deck. So we first off append our root and I append the height. So I keep track of the height. I say 0 here. The reason I keep track of the height is because I need to collect everything at the same height together. Like everything at the same height has to be. Oh, I don't know what just happened. It has to be in the same list. Okay, so everything with the same height has to be in the same list. So like 15, 7, both 15 and 7 are at the same height in the tree. Kind of like that, so that's why I keep track of the height. So I use a tuple. So the height starts out at 0. I create this temp thing, really just because I couldn't come up with a better name. Actually, I don't even use it. Oh no, I do use it. I use it right here. Alright, okay, yeah, and then I iterate through it. Yeah, so here I'm going through my queue. I get my node and my height by popping from the left, and by popping from the left, that means I'm using FIFO. I'm getting the thing I added into my queue first, because I'm appending to the right, is also what I'm going to look at first. So then I just append the node.val and the height. It makes sense. And then I check the left and the right. So like up here, if I was at the 3, I check the left and the right, so the 9 and the 20. And I'd see that the 9 is not none. So I'm going to add it to my queue and add that increment the height because we're going down 1. So these both will have the height of 1, and I'll append both of them, and then you can kind of see it. So when we go to 9, it will say none for both of these, so it won't do anything. But for 20, it will add 15 and 17 with a height of 2. And then we go down here, so this fills in my temp, which will be a list of tuples containing the values, and the heights. And then I go down here to my next part of code, which is the purpose of this code is to use the height and anything with the same height, add them together. So I create last h. I just initialized it to be -1, but this is like what was my last height value, and these are res and ants. You'll see. I'll just go over what they do. So I look at for t and temp. So t and temp is just we're iterating through our temp list, our tuples, and we check t of 1, which is the height. And if the height is not equal to the last height, then we're going to want to do something. So like this will happen for the first one, but we're not going to append anything to our res because, well, our answer is empty. So we set our answer to empty, and then we append the value and we reset our last h. So as long as last h is equal to the height, so like since 50, wait, yeah, oh yeah, since 9 and 2 are at the same height, they're gonna have, they're gonna be appended together into one answer, and then like once you reach a different node with a different height, it's gonna like check and basically append your list, because answers a list, into your result. So you have a list of all the node values at the same height appended, and then you just keep going through this for loop. Now at the end of this, you might end up with something left over in the answer. Like answer may still be not empty. If that's the case, you need to make sure that you add the answer to the result if it's not empty. And then I just reverse it and then return res. So if I look at time complexity, going through the while loop here, going through the binary tree, because the binary tree is not necessarily balanced, it could be skewed. That I think approaches O of n time complexity for worst case. The best case is if it's balanced and it'd be O of log n. But then again, because it's a BFS, it's not even really O of log n, because I'm still gonna have to go through every element in the tree. So I feel like it's always O of n, because I'm always going to go through every element in the tree here in this BFS search. BFS search is basically not exhaustive. It doesn't like exhaust one route and then backtracks or whatever. I don't even know what I'm saying. That's making it more confusing probably. But anyway, so here the time complexity for this is O of n, and the time complexity for reverse is O of n. So yeah, so the time complexity is about O of n. The space complexity is about, it's probably O of n as well, because I'm just storing stuff in these data structures. And here, so temp might be O of n, res might be O of n. So that's that's like O of 2n, which is still O of n. So yeah, so that's what it is. I guess I'll submit it again. I've already submitted it. It does pass. We can look at more details, I guess, to see just how fast it was. And so after I look at this, I'm going to, it's actually pretty fast, it looks like. So yeah, so after this, what we're going to do is, I'm going to look at discussion and see if there's a better way to do this. So this was just my code that I came up with, but I'm going to go analyze the discussions and see what's going on there, and then see what can be learned from that. So actually, let's just go there. I'm not even going to stop the video here. Okay, that's a question. Is there any better idea than doing regular level order traversal and reverse the result? This is a question. Well, okay. Let's see. I went back to the classic questions. Let's, oh, you know what? I always notice that discussion is harder to, like, sort. I guess I could sort by most votes. This one has the most votes. So let me open up this one. Open up this one. Okay, not that many people use Python, apparently. And then sort by, okay. Alright, so I'm going to finish this problem up. So I look at discussion, I found an easier way to do this problem. This is how many lines of code I used. It's a lot of lines of code. So there's an easier way to do this problem, in which I'm going to do it live, because I think I have it memorized. It's not that complicated. So we start with creating res. So we start by creating our queue and res. So we have a deck, and we want to add into our deck, we want to add root and 0. And we want to add this. We want to return res. And do something like while queue. So while queue, we want to do some stuff. So we know that if we want to pop, right? So we want to do node and node and I was calling it height pop left. So we pop left and we say if node. So it depends if node is none, we don't really care. But if node is not none, you want to do this. We want to do q.append node.left. This is kind of interesting, but yeah, just basically always add on to the thing. Even if it's none, you add it. You'll add it into the thing. Height plus 1. Okay. So this makes sense, right? So like, as long as the node is not none, we're going to look at its left and right, because it could have a left or right child. If the node was none, it can't have a left or a right child. It's impossible. There's also other stuff we want to do. We also want to figure out what we're going to add. So we're going to do res at our current, whatever height we're at, dot append node.val. So what this should do is it should take the height. So if the height is 0, it should append it to the thing at 0. Now the only really tricky thing is I haven't initialized something. So we could do this. We could say if not res at the height. I think this will work. This might not. Let me check something out real quick. Let's say we have, and then say Q0. It gives you index error, doesn't it? If not, I don't think you can do this. Yeah, you're gonna get index error, obviously. Okay, well, so you have to do something different. You can't do like if not. So what you can do is, there's a trick here, where if height is equal to the length of res. So you just think about this. So initially, our length of res is 0 and our height is 0, so it works. If we do that, then we basically do res.append we append this thing at this level. So now when we use height is 0, it's going to give us this empty list at the 0 index, and then I append onto that, and then once the height goes up to maybe 1, well, it'll be equal to the length of res, because length of res is 1 at that point, and then it's going to append on to there, and what it's going to append on is basically the empty list, and then it'll start appending on node vals into that empty list at index 1. So it's going to do something like this. It's going to start with this. So I'll look at what res is equal to. So it's this, and then it should add on something like this, because the height will be equal to 0 and it's equal to the length of res. Length of, I'm just trying to figure out what okay, it is 0. Okay, empty list is 0. Yeah, it makes sense. So then it's going to go to, we add in the node value, which is 3, and then we go to height is 1, and height is 1 is equal to, so it's going to add in a new empty list, because height is equal to the length of res. And then we're going to append on our value, whatever it is. It might be, I guess it's 9 here. It's 9. And it's going to append on the 20, and then it's going to create a new empty one at height equals level 2. So then all we have to do is return. Okay, so we could do res.reverse. We could do that, but in Python there's a clever way to do something which will return it. You can also just do this to return a reversed array. Okay, submit this. Blah blah blah. We want more details, and when I go more details, it's actually quite slower. Interesting. I mean, so So apparently, this solution is quite slower than the solution I had, but it is not very verbose though. It's also very simple. Yeah, I wonder why it's slower than mine. And my original solution, ooh, that's even slower. Oh boy. I think it has something to do with the fact that it's, yeah, so I mean, I think if you want to make this better, you could do this. Or make it faster. I'm just going to make it a little faster real quick. I think this will work. Okay. Right. It won't work with the empty. That's fine. Oh, that's okay. You know what? I know how to fix this. That way it'll check if there's a node. Indentation error? Wait, what? Oh, I see. Accepted. Let's see if it's faster. It's not that much faster. Okay, so I think I wasted some time, so I apologize. This video just went over the time that I wanted to do. Kind of got distracted. But I mean, so the interesting result is, yeah. So I did this code two methods I use, basically using the same idea though of tracking the height. But yeah, yeah.